Welcome, this is Mrs. Nearing. In this video we are going to be talking about the reaction quotient Q and how that can be used to predict the direction of change in a reaction. You're basically using it to predict whether a reaction is going to proceed to the right or to the left, and we're going to go through some practice problems related to that and just general Q versus K problems and also applying it to Ksp. So let's take a look at this first problem here. We have a reaction and we're given a Kc value for this reaction. So first thing I'm going to do is I'm going to write out a Kc expression for this reaction. So C is concentration. So even though these are gases I'm dealing with, we're going to describe their amounts in terms of concentration, molarity. And notice that in my K expression, I leave out S because it is a solid. So I leave out solids and liquids from my K expression. To find Q, the way that I solve for Q is I just plug the values into my K expression. So I'm just going to plug in the given molarity of H2S, which is 0.483, divided by the given molarity of H2, which is 0.762. And when I plug that into my calculator, I should get 0.483 divided by 0.762. I get 0.634. So what does that tell me? This number will tell me whether or not I am at equilibrium. If Q is equal to K, then I am at equilibrium. If Q is less than K, then remember K is products over reactants. So if my ratio is not big enough, that means I need more products. In order to reach equilibrium, my Q value needs to get bigger. So I'm going to get that by making more products. So that means my reaction is going to proceed to the right. If Q is greater than K, that means I've got too many products. Okay, too many products. I need more reactants, so the reaction is going to proceed to the left, using up products and turning them back into reactants. In this case, my Q is less than K, because K is 10 to the 5th, and this is just 0.6, so it's a lot less than K. So I need more products. So my reaction is going to proceed to the right. That's how we describe that. So again, let's write that out up here. Boom. So I need more products, the reaction is going to the right. Looking down at a problem like this one, you're going to write your Kc expression. So that's H cubed CO divided by H2O and CH4. When you are solving a problem like this, notice how this is a Kc expression. We are given a Kc value. We know that it's 4.7. So when we are solving for Q, we need to make sure that the values that we plug into my expression are molarity values. That's really important. So for an example of H2, I'm not going to plug in 1.7 moles of H2. I'm going to say 1.7 divided by 2.5 liters, and that's going to be cubed. And with CO, it's going to be, what, 0.6 divided by 2.5 liters. And water is going to be 0.2 divided by 2.5. And the other one, my methane, is going to be 0.5 divided by 2.5. And these values, just like K values, are always going to be unitless. You should find in this case that Q and K are equal. So I'd say, yes, we are at equilibrium. Because Q is equal to K. Looking at problem 3, this one is a Kp problem, so you need to make sure with Kp values you are plugging in, whoops, what happened here? Okay, sorry about that. So you're using a Kp value, so you gotta make sure the values are in atmospheres. You gotta make sure you're using pressures. Okay. Now let's look at one that is an application to a Ksp scenario. So if someone, this is the kind of scenario would be, someone says you mix these two things together and we say, does it precipitate form? So the same rules apply. You're going to, if you're trying to figure out which way a reaction is going to proceed, what you're doing is you're comparing Q versus K. And if Q is less than K, reaction will proceed to the right. If Q is greater than K, the reaction will proceed to the left. So let's take a look at this scenario. We're going to write the Ksp expression for the dissolving of barium sulfate. So it might help to write out the reaction first. So solid barium sulfate is going to break apart into barium ions and sulfate ions. So the Ksp for that, remember products over reactants, but the reactants are a solid, so they get left out, is going to look a little bit like this. So that's our Ksp. So there we go. You might notice that this, in this context, this might stand out to you, that my dissolving reaction is actually the inverse of the precipitation reactions we've written before. Okay, so it's basically the opposite of a precipitation. So now let's figure out what our let's figure out the concentrations of barium and sulfate ions. And you might say, wait, why is she asking me to calculate that? Aren't I given the molarity? But what happens here is, like we've seen happen in several labs so far, is when, in order to make this reaction mixture, we actually are mixing two solutions together. So we're mixing together 210 mils of 0.0475 molar barium ions. I'm going to ignore the nitrate because nitrate's a spectator. And I'm mixing together 315 mils of 0.45 molar sulfate ions. I'm going to ignore my lithium because lithium's a spectator. Here, I'll cross it out just for fun. They're there, but we're ignoring them because they're spectators. So to find the true molarities of barium and sulfate, I need to figure out what their new, diluted molarities are. So I mix these together. My total volume is actually 525. So to figure out the molarity when I dilute something, I'm going to use my dilution equation, which is M1V1 equals M2V2. And I have to do that both for barium and for sulfate. So for barium, it's going to be 0.0475 times 210 mils, and then X 525 mils. So we'll find that my barium concentration is 0.0190, and then for my sulfate, it's 0.450, and I've got 315 mils, and then X, so I have 525 mils. So we'll find that my sulfate molarity is 0.270. Okay, so now that I've got my true molarities of barium and sulfate, I can plug that into my K expression and solve for Q. So Q is just going to be my barium times my sulfate concentration at a given point in time. So my barium is 0.109 molar, and this is 0.270. And if I stop and solve, I get 0.0051. So that's my Q value. And I want to compare it to K. K is 1 times 10 to the negative 10th. So it looks like Q is much bigger than K. That means I've got too many products. That's how I think of it. It's too big. I got too many products. That means the reaction is going to proceed to the left. And if I think about what that means, look back up here at my reaction, proceeding to the left means that you make the solid, which we call the precipitate. So the question asked me, will I form a precipitate? Yes, because the reaction is going to proceed to the left because Q is greater than K. So that is how we would solve this type of problem. One other thing I want to say is a lot of people on this type of problem, they'll say, will a precipitate form? And people will answer yes, because barium sulfate is insoluble. But what we want to acknowledge is when we say that things are insoluble, really, like, that's just everything's a little bit soluble, right? So barium sulfate will dissolve a little bit. So to figure out whether something will truly form a precipitate, we actually have to consider their concentrations, and we have to compare Q versus K. So, yeah. Thanks for listening.